Good evening. Thank you for coming to today's seminar. I am Jiwon Park, and today I will talk about the next frontier of visual navigation, from diffusion to Gaussian splatting. In this presentation, I will mainly talk about the visual navigation that uses only a monocular camera, and we will cover what visual navigation is, why it is necessary, and how its methodologies can be classified. And then we will examine how approaches using diffusion and Gaussian splattings are classified and what the key ideas within there are. Let me start with a research map of scene representation for robotics, and this diagram is based on the material from Professor Luca Carlone's seminar on next generation robot perception. And based on these tasks and requirements, scene representations can be categorized along three primary axes. And the first one is robustness. The goal here is to reconstruct metrically accurate scenes, and second one is scalability, and this axis considers the complexity of the scene size and the requirements for supervision or data labeling. And the third one is autonomy or scene understanding, and this relates to the level of high-level task specification a robot can handle. For example, understanding our natural language commands like "Robot, go grab me the cup of the coffee on the desk" is much higher level of autonomy than simply following a geometric instructions like "Robot, go to the position XYZ." And different representations occupy different positions in this space. 3D point cloud maps excel in robustness and scalability, and 2D semantic scene graphs provide rich semantic understanding, and each approach offers distinct advantages depending on the application. It is this axis of autonomy and scene understanding that represents the next major challenge and opportunity in robotics. Moving beyond simple geometric tasks, we aim for robots that can truly comprehend their environment and perform complex, high-level objectives in the real world. This brings us to the visual navigation, where robots must not only perceive the environment, but also reason about it to accomplish meaningful tasks in the real robot settings. Visual navigation enables robots to reach specified goals using camera observations. Goals can be specified as target coordinates, or reference images, or object categories, waypoint sequences, and semantic commands like "find the cups." Each approach requires different levels of scene understanding. A recent survey on visual navigation identifies 4 fundamental questions in this field. Among these, the most critical challenge is how can we extract explicit or implicit information from monocular camera observations that enables robot navigation. And this environment representation problem is central to effective visual navigation. Visual navigation methods can be categorized by how they process visual information into actions. And the first one is embodied AI approaches, and this directly maps visual observations to actions in an end-to-end manner. These methods can learn navigation policies through interaction in photorealistic simulators, minimizing the need for explicit geometric representations or handcrafted components. And second one is geometry-based approaches, and this explicitly extract geometric information like maps from images. And then apply traditional plotting algorithms. And each approach offers different trade-offs between interpretability and data efficiency and generalization capability. And in this seminar, we will explore 2 representative methods. The first one is diffusion-based visual navigation as an example of the embodied AI approach, and 3D Gaussian splatting maps as an example of the geometry-based approach. In simple terms, diffusion models work by gradually adding noise to data through a forward process and then learning a reverse process to recover the original data. Through this, diffusion models can model high complex data distributions with strong diversity and robustness. After DDPM was introduced in 2020, diffusion-based planning papers quickly gained popularity. As an example of embodied AI-based visual navigation, I'll introduce VINT from Berkeley AI Research. VINT is a foundation model designed to work across different robot platforms, and it takes past observations and a subgoal image as an input, and outputs the estimated time to reach the goal and a sequence of future actions as normalized waypoints. VINT argues that navigation is fundamentally different from recognition. Recognition asks, what am I looking at? Like identifying objects like, this is a kitchen. But navigation asks, how do I transform my state to reach the goal? And this distinction is crucial. Late fusion architectures, which encode observations and goals separately before combining them, behave like recognition systems, learning absolute features. And VINT instead uses goal fusion, fusing the current observation with the goal image before encoding. And this forces the network to learn relative transformations. Given where I am and where I want to be, what kind of changes are needed? And VINT employs two encoders, the observation encoder for past frames and a goal fusion encoder that jointly processes current and goal observations. And this architecture learns the relative relationships essential for navigation. And the second major challenge in visual navigation is handling long horizon tasks, and VINT addresses this through hierarchical planning. For distance goals, VINT uses a diffusion model to generate intermediate subgoal images, and the system first generates a sequence of visual subgoals leading to the final destination, and then uses the goal fusion architecture to navigate between consecutive subgoals. And this kind of hierarchical approach breaks down complex long-range navigation into manageable short-horizon steps. VINT's training step is quite straightforward, and the system samples trajectories from the dataset and selects the current time step and a future time step between 0.5 to 2.5 seconds ahead, and then predicts two outputs, a sequence of 5 future waypoints, and the temporal distance to the goal. The loss function combines action prediction and distance prediction with a weighting factor lambda. And this kind of self-supervised approach requires no manual labels, because future observations naturally serves as goals. And the distance prediction auxiliary task particularly helps with hierarchical planning for long horizon navigation. The result shows that VINT can generate paths regardless of the robot platform, so it can be served as navigation foundation models due to its architecture focusing on the relativity. And the second part is Gaussian splatting as an example for the geometry-based visual navigation. As an example of geometry-based visual navigation, I will introduce approaches using 3D Gaussian splatting. Gaussian splatting represents scenes as collections of 3D Gaussian primitives, each defined by position, covariance, opacity, and color. And this explicit representation enables direct integration with traditional path planning algorithms while maintaining high-quality visual rendering. And after 3D Gaussian splatting has been introduced in 2023, lots of methods that uses Gaussian splatting emerged. But in the field of navigation, the uses of Gaussian splatting has not yet fully discovered, and the research are still going. The main challenge in using Gaussian splatting for planning is extracting reliable 3D geometry for collision tracking from visual representation. And to address this challenge, I will introduce two recent papers that tackle the problem of obtaining collision-free geometric information from Gaussian splatting representations. Rather than covering all details, I will focus specifically on their collision checking methodologies. Without proper geometric reconstruction, you will end up with maps containing holes and gaps, making path planning impossible. In the first paper, RTG SLAM, which stands for Real-Time Gaussian SLAM, separates Gaussians into two types. And the first one is opaque Gaussians for geometry, and the second one is transparent Gaussians for visual rendering quality. A fundamental challenge with Gaussians is defining collision boundaries. Since Gaussians are continuous distributions without clear edges, RTG SLAM addresses this by treating opaque Gaussians as ellipsoid disks on their dominant plane. Instead of alpha blending depth like standard Gaussian splatting, it computes depth from a ray plane intersection. This allows a single Gaussian to accurately represent flat surface patches with consistent depth values, and this kind of approach makes collision checking feasible for planning. And the second paper, High SLAM, takes a different approach by incorporating monocular depth estimation as a prior during map construction. And this produces geometric consistent maps that are significantly cleaner and more suitable for planning. With such high-quality Gaussian maps, path planning becomes quite successful. Additionally, Gaussians offer extensibility, and they can be augmented with semantic information, enabling more intelligent navigation behaviors beyond pure geometric planning. And in summary, visual navigation enables robots to operate in dynamic, unmapped environments using camera observations. We explored two approaches, and embodied AI methods like VINT learned end-to-end policies without explicit mapping, but require large datasets and operate as black boxes. And second one is geometry-based methods, and this kind of approaches using Gaussian splatting provides an interpretable, controllable representations, but they need a mapping phase and they face collision checking challenges. And each approach offers distinct trade-offs between learning efficiency and geometric precision. This is the end of my presentation, and thank you for your kind attention.